Hello everyone, this is Amir from Audio Science Review, continuing the series I started on explaining in detail what the measurements show for each category product. I thought I'd get into power amplifiers. I've been testing a ton of them as of late, and I thought it would be a good next one to do after the speaker measurements that I just did a few days ago. So let's get into that. Hopefully you know what a power amplifier is, or integrated amplifier is. It's a device that you feed it line level inputs, whether it's XLR or RCA inputs, and then the output is obviously speaker terminals, binding posts. Sometimes there's terminology confusion. People are into headphones. They hear the word amplifier and they think headphone amplifier. So I call these usually power amplifiers or speaker amplifiers, although by default, if somebody says an amplifier, they mean speaker amplifier. So I'm going to walk us through a recent review that I did and explain what each one of the measurements show. In this case, it's a new amplifier from Topping called the LA90 Discrete. They used to have an IC version of this, and the parts disappeared. They couldn't get any more of the components. So they had to switch and do their own discrete version of it, which usually results in worse performance, even though it should theoretically allow you to do better. A lot of companies that do discrete implementations, unfortunately, they go backwards. Anyway, this is a compact desktop size amplifier. And to keep the size small, they have this giant sort of Xbox class laptop power supply externally that you plug it into. It's got this nice custom terminals that screw in, so it's quite stout and nice, but you do have to find space for this big brick. Usually, typical of my reviews, I note things like this, but I don't do extensive functionality review for that. You should go and watch other reviews or just look at the user's manual. Anyway, all of my amplifier reviews start with what I call a dashboard. The dashboard starts with driving 5 watts of power. That's what this is, 5.049 watts. Into a 4 ohm load, what we call dummy load. Is basically very large resistors that can dissipate a lot of power. And the signal that we drive into the amplifier is 1 kilohertz. Why that? Well, traditionally that was what was picked. Turns out perceptually, the harmonics of 1 kilohertz, if you look at this as a 1 kilohertz tone, the harmonics land at 2, 3, 4, or 5 kilohertz, and our hearing is most sensitive in this region. So it's actually not a bad choice, although I doubt that it was picked for that reason. It was probably easier to make a 1 kilohertz oscillator in the old days that was accurate than not. So anyway, we follow that. Now, I do deviate from the typical practice in that standard amplifier measurements use 1 watt. As far as the output power. I don't like that because in modern times, speakers have become a lot less efficient, a lot less sensitive, and 1 watt doesn't get you far at all, number one. Number two, if you measure amplifiers 1 watt, you're basically measuring their noise performance. Their distortion is so low for a good amplifier that it just gets lost. Whereas at 5 watts, there's a shot that you actually will see some distortions, and indeed, we're seeing that distortion over here. So in this graph, this one spike is what is expected, is this sine wave that you see on the left, and everything else is extra, that unwanted, if you will. Here we see the harmonics, which means multiples of our tone. So we put in 1 kilohertz, so we got the 1 kilohertz out, but we also got a 2 kilohertz, 3 kilohertz, 4, I think we skipped over 5, then we had 6 and 7, and keeps going on. The good news is that if you look at the amplitude of these spikes and go all the way to the left, you see that the worst case one is as minus 125. Threshold of hearing is around minus 115. So even if this tone wasn't here and all we heard was a distortion, which is not going to happen, but stay with me, these distortions would be provably inaudible and for 5 watts. And so they're not of any consequence. From engineering excellence, we like to see 0 distortion, but it's not going to happen always. So these distortion spikes are, we see them. Our instrumentation is quite a bit more sensitive than our hearing, but we know and we can prove that they're 100% inaudible in here. There's a little bit of power supply noise here at 60 hertz. We're in 60 hertz country in the US. and that's at -145, which is just crazy low and not anything to worry about. And by the way, sometimes this is an instrumentation issue. With real speakers, you won't see it. So this is where my eye always goes when I first start this dashboard. I look at this called the fast Fourier transform. It's basically, if you took this sine wave and decomposed it, you get one giant sine wave like this, which is what you see. But also little sine waves are mixed up with it, which you cannot see in this oscilloscope type of display. So you must decompose this into its components to be able to see the contributions from power supply noise and so forth. If we take all these distortions and add it to the noise, and this is not the true noise floor, the true noise floor is about 35 dB higher. But if we took that, the exact correct value of it, and add up the energy of all of this, and took a ratio of that relative to our signal, and consider our signal 0, we can compute what is called THD plus N. So what is the ratio of all this bad and unwanted stuff to the signal that we do want, which is 1 kilohertz. And you get this crazy small number with, percentage, which is called THD plus N ratio, which you're never going to know or remember, and it's just terrible value to look at. Fortunately, we can take a log of that and change the sign, and we get a number in decibels, and that number lands around 120 dB. So what does 120 dB means? It means the sum energy of the noise and distortion is at 120 decibels lower. I mentioned that 1 is 115. We're in full transparency, so this amplifier is 100% transparent to the source as far as your hearing is concerned. I've measured about 210 amplifiers to date, the standalone amplifiers. I've measured another 30, 40 that are part of AVRs and other kind of products. But as far as standalone amps, I've got that. And if I slot this number into what the sign ad is for all the other amplifiers that I've measured, it's a long list, and I'll show you the example of that with all 200 of them. But here we see that this one ties for number 2 position or number 1 position with the IC version of the same thing. So Topping LA90 is currently at 120, and the next one down is 7 dB lower, and that's a giant gap. Even though audibility is the same, it's just for us engineering accomplishment. This is superhero stuff to be able to get the noise and distortion to be this low. So right away we know that we're dealing with a design that's gone through incredible scrutiny and incredible skill to be able to achieve this low level of noise and distortion. One note to make, very important note about sign out. A lot of people complain, they say, well, this, the bigger the number doesn't tell me that, it sounds better. It actually does, because remember I said this number is the sum of noise and distortion. I've already told you that distortion is almost -130. So the thing that drags the sign out from 130 to 120 is noise. And to the extent the noise floor is 120 decibels lower, that means you can play music at 120 decibels and the noise floor would essentially be inaudible. You really need to go to -5 dB. So a lot of people, even with state-of-the-art amplifiers, you can hook them up to speakers and stick your ear next to a tweeter and you will hear some hiss. So this is not a bogus value if you care about hiss from your speakers, especially if they're sensitive. Okay, this amplifier, like many others, comes with 2 different gain settings. One of them is very low, which is this low gain one. It's has a gain of 9.3 dB, which is quite low. And then it has a high gain, excuse me, that jumps up to 20 dB. In the old days, typical gains was 25 to 30 dB. That's way too much gain for today's world. Today's world, our desktop DACs and regular high-performance DACs can output up to 4 volts or more from their balanced outputs and 2 volts from RCA, and you don't need that much gain. So this 19 dB gain is plenty. And by using lower gain, you can actually improve the noise performance of an amplifier. Excuse me. And I'll show you that in a second. So, but be mindful that to get power out of this amp with 9 dB gain, you need to have basically a professional audio interface that goes up to 8 or 9, 10 volts sometimes to be able to get full power. Unfortunately, there's no standardization in amplifiers. Every company picks a different number for gain, and it's a bit of a crapshoot how you can drive them on this thing. But if the performance is good at high gain, then go ahead and use that, and just about every source can drive. Okay. So I then measured just the noise performance. Here, the noise and distortion were mixed up together, but we can parse that out. And first at 5 watts, we see that it's got 125 dBs dynamic range. So that means you can, again, play at 120, 125 dB, which is reference live concert level loudness, and your noise floor will be at 0 dB. So very, very, very quiet. And that's only at 5 watts of playback. If you let the amplifier go its full power, it now reaches 137 dB. That's equivalent to 23 bits of resolution or dynamic range. And that's just incredible. This power amplifier is acting like a DAC would, which outputs very low power. So this kind of performance is just insanely good. But note what I've put in here, that you need 6.3 volts in low gain to get maximum power. So typical DACs, again, to stop at 4 volts or 5 volts. So to get the max power out of this thing in low gain mode, you need to have 6.3 volts of output. Fortunately, you can switch to the high gain mode, and if you did that in high gain mode, now you only need 2 volts to get maximum power, which every balanced output more or less can generate. But high gain costs you some noise penalty. We see that we drop 5 dB. But hey, 120 dB, which is 20 bits of dynamic range, is already superb. And 22 bits of full power is just fantastic. The music you listen to, best case, about 18, 19 dB of dynamic range anyway. So what this means is that this won't add to that noise. Okay. Frequency response used to be in the old days. We struggled to have flat frequency responses, but today is basically expected to get a flat audible frequency response flatness in here. Means between 20 and 20 kilohertz there's no deviation, and ideally we want it to be flat even below 20 hertz, so go down to 10 hertz to have subsonic rumbles or something, let's say in your LFE channel coming out for your movie soundtracks, what have you, or even music on this thing. I measured at 4 and 8 ohms, and ideally they're the same, and they are in here. I'll show you an example of when they're not the same. But you want to see an amplifier that doesn't change its frequency response depending on the load. If I had a tube amplifier with a high output impedance and I change these things, you will indeed see oddness and changes in here. Crosstalk usually is not an issue. Crosstalk is a notion of how much signal from one channel bleeds into the other channel. For us to have a sense of separation, we only need 40, 50 dBs on this thing. And so anything more than that is gravy. Here I've got 2 references for you. One is this $25 LePi amplifier. Literally costs $25, and you can see its channel separation over here, and gets pretty poor at high frequencies. At 20 kilohertz, it's only 30 dB of channel separation, but it goes down to 60 dB or so at 1 kilohertz. And then state of the art is this benchmark HB2, which is down here. By the way, the IC version of LA90 actually beats the benchmark. For some reason, I got higher value in here. I probably should go back and retest to see what happened here. It's odd for it to be this high. Most amplifiers actually worsen this topping. They're somewhere in here. So, but again, audibility is fine. It's just that from engineering point of view, you want this to be as close as you can to down here. People usually complain and say, oh, all your tests so far have been one frequency and music is not one frequency. So how about that? Well, we have a test signal that we call multi-tone, has 32 tones in here, and they're all mixed together. So always sine waves. So if you look at it, it just looks like random stuff. And it actually sounds like organ notes that are being played simultaneously. When we play this is, I set the maximum to be 0, so 0 is the reference. And then what we hope that the bottom basically falls off this graph, ideally, meaning that there is no noise or distortion, allowing this bottom to be infinitely low. Nothing's going to be that way. But fortunately, this device, this amplifier, Topping LA90 discrete, does superbly well. I usually just eyeball where these are all intermodulation distortions, by the way. So these are distortions that are created as a result of each one of these things generating harmonic distortion, and they get summed together to this. And if I eyeball it and convert that to decibel, convert that to bits from decibel, which is just dividing by 6, I get 21 bits of distortion free at 5 watts. So this is, again, the distortion is just well below your music and your threshold of hearing. Just shows how great this is. The other thing is that it shows that the distortion level doesn't change with frequency. I'll show you other amplifiers where this thing can climb up, or the low frequencies can climb up. So you can see a pattern in here, and this kind of pattern is great, which is that the value is low and is frequency independent. Okay, now all this stuff is good, but there's a secondary things you want to care about. The number one thing you usually care about amplifiers is having more power than you ever possibly need. Let me repeat, you want to have more power than you possibly need, and you always need more power than you think. Most people have very wrong impression of how many dBs they're actually playing, and they keep thinking that they're listening at 70 dB or whatever. That's just never the case. 70 dB at 20 hertz is completely inaudible. So if you're hearing bass down that low, you're way above 70 dB. So nothing distorts more than an amplifier that has clipped, which means that it's reached its maximum power, can't go any higher. And you can see an example of that. The moment this amplifier clips, look at how distortion shoots up, and this becomes instantly audible. It's crackling, garbling, muting. So you want to avoid this. You don't want your peaks to hit it, and certainly not your average on this thing. So I always plot this. And along the way, so this is a sweep. Basically, I changed the input signal from very low levels to the point where it causes this clipping. So naturally, we see some kind of response in here. This LA90, the reference in here is a benchmark HV2 again, which is this dashed blue line that for the longest time no amplifier could beat. But now we have this $600 amplifier outperforming it on noise level. This part of the graph that's pointing down, as we increase power, it gets better and better, means we're just seeing noise, the impact of noise. Until the graph starts to point back up, that's when we know that distortion starting to take over. So up to this point, almost to max power, this amplifier is basically noise limited. Its distortion is just so low. And what noise it has beats my best case reference. So it is way into state-of-the-art, class-leading type of performance over here. The drawback for this amplifier, though, is that it only produces about 70 watts. So the benchmark, on the other hand, produces 163 watts. So 70 watts is not a lot of power. I'll show later on that you can bridge this amplifier and get more power out of it. But here you're getting incredible accuracy. But this is not a powerhouse type of amplifier. It's medium level of power, if that. Now, where I put this cursor in here, it sort of approximates these measurements jump from point to point in here. Doesn't have infinite resolution. So sometimes this point is not very accurate. And at any rate, this point in this amplifier may be way down here, way up here. For example, here we see that the benchmark was a little bit lower distortion. Another amp may have a curve that's up here. So it becomes rather unfair to compare where the clipping occurs. For that, I've created a standardized test where I measure how much power we get into the same condition. This is 4 ohm, by the way, 4 ohm load, and 1 kilohertz. But we measure how much power we get until we hit 1% total harmonic distortion. And where did 1% come from? I picked it as a probably reasonable value that's inaudible to many people. It won't be inaudible for everybody, but I sort of picked as a reasonable value that maybe your peaks can hit it and be okay. But by measuring every amplifier at 1% now, this number is comparable to other amps. So you can take this number, and if another amp puts out 150 watts, then great, that amplifier's got more power. The amplifier specs are a nightmare in this area. Every one of them's got made up power numbers. So you want to ignore anything that the manufacturers tell you. unless they show you this graph or this, what they're telling you is completely bogus. And some of them get crazy bogus. You can buy a $300 amp that advertises 6,000 watts. So don't go by those things. We must measure. If we don't measure, you don't know what you have in an amplifier. You absolutely do not. So we got to do this. Now, some people say, well, that you're measuring an amplifier with a continuous tone. Music has dynamics in it, and bass note comes and goes boom, and it goes away, maybe lasts 20-30 milliseconds. Maybe the amplifier produces more power if you let it do that. Indeed, amplifiers have a power supply with a reservoir capacitor that for short duration is able to produce more power than it can continuously. So I have designed a second test that complies with this standard called CE 2006 490A. It was designed to try to corral the car amplifier guys who go nuts with these specs. And it is a burst sine wave, sort of goes up and comes back down. And, it complies with the specification. Go look that up. But I picked 1% again for consistency with this number. So, and we can see that short term, this amplifier can produce 93 watts versus 86 watts in more continuous power. Not a whole lot of headroom. You will see a lot more headroom when I measure 2 channels out of a, let's say, 9-channel audio-video receiver. They'll have a giant power supply designed to power many amplifier channels, but if you're just measuring 2 channels, you're able to get a lot more headroom out of them. So oftentimes you can get 20-30% headroom out of those things. More headroom is better because that means you won't hit that clipping point as easily. So that was 4 ohm. You should know that about 80 to 90% of the passive speakers I test are at 4 ohm or 3.5 ohm or 4.2 ohms. They're all within this 4 ohm region. I'll show you 8 ohm, which used to be the thing that we always looked at in the old days. But just know that, if you don't know any better, and I published the impedance for speakers that I test, but if you don't know, just assume it's 4 ohm. And again, those companies lie, the speaker companies lie about the impedance for the most part. So just assume 4 ohm, and this is basically the power you're going to get. But just in case you do know and you care about 8 ohm, I measure that too. When we go up to 8 ohm, our power drops because the impedance, the way we compute power is that the voltage squared divided by the impedance. And if you double the impedance, you basically get half the power. So we can see the power drops to only 41 watts on this thing. So not a very powerful amplifier compared to tube amps and things like that. It's still a lot of power. But in general, you do lose something. Here I have a reference of another great amplifier, Class D amplifier by a company called Purify. And you can see its performance over here is this dashed blue line, and there's this massive improvement in noise figure for topping in here. So it performs very well, but again, it can't compete on available power. Okay, now this graph is not very revealing. It's actually very good that it's not revealing. I'll show you where it normally, what it normally looks like. I said that this is at 1 kilohertz. This is what our power sweep looks like at 1 kilohertz, but we care about what power at lower frequencies, or we care about power at higher frequencies. So I actually run these sweeps into 4 ohm, but I do it at all these frequencies from 20 hertz all the way up to 20 kilohertz, although I don't always show the 20 kilohertz one. Usually stop at 15 kilohertz for reasons I won't get into right now. And ideal amplifier would have all the lines on top of each other, and indeed that's exactly what we see in here. Basically, this amplifier does not care what frequencies you tell to play, except when you get down to 20 hertz, you lose power, and this happens with every amplifier that I test. So all at higher frequencies, it actually has more power than at 20 hertz. 20 hertz, the sine wave moves so slowly that it sucks all the juice out of the output capacity, the power supply capacitors, so it winds up clipping sooner. And so a lot of times people say, low power amplifier is good enough. I don't need more than 50 watts. Well, yeah, 50 watts, remember, that's at 1 kilohertz. What does it give you at 20 hertz or 30 hertz or 40 hertz? It may be half of that on that. So you got to be careful when looking at that. This is a more recent test that I've added. I think it's a useful thing to run, which is what happens if you turn the amplifier on and what happens when you shut it off? Does it make any kind of noise? And I started to measure that. So what I do is that I start with the amplifier off and I start recording it. So ignore this time thing. It's basically a running measurement of what am I seeing out of an amplifier, as just as if you hooked up a voltmeter to it. So when it's off, it's got this very low 2 microvolts of noise coming out of it. At this point, I've turned on the power button, and indeed it creates a glitch. The glitch, though, is not even 1 millivolts over here. So this is probably not audible on this thing. Now, you could have an ultra-sensitive speaker and it could make it audible, but anything less than a millivolt likely not audible. So, but after the glitch is done, it goes back to its idle level noise. And so I let it run, and then I power it off. And the power off, it actually generates a larger pop. And now it gets up to 3 or 4 millivolts. And that may be audible in some speakers, you know, and not on others. I've measured others that are much worse than this. And then once it shuts off, it goes down to, you know, where it started. So if you care about that, you know, some people are quite annoyed with the pops that they hear when they turn on and off. So amplifiers are really bad in that regard, and worry about even damaging their tweeters. You know, you want to pay attention to this on this thing. The other test I run with amplifiers is that I don't just turn them on and measure them. I let them warm up and stabilize. On this amplifier, we got an odd response in that one channel was stable as a rock, it didn't care, but the other channel actually was a little unhappy and then became happy after about 40-50 seconds. This tells you whether leaving an amplifier on will do you any good. I'd say 50% of the time I find that the performance gets worse as the amplifier warms up, not better. So a lot of people think, oh, it's like my car engine needs to warm up. Like, no, it depends on the design parameters. Sometimes when components get hotter, their noise level goes up, and they don't always behave that way. But this is an exceptionally well-engineered amplifier and becomes stable, like I said, instantly in one channel. The other one took a little bit of time. Maybe other samples won't do that. So extremely good. But, you know, if you want to be anal about it, leave it on for a minute and you'll get the best performance on this. Not all amplifiers allow bridging, but this one does. So I went through the work of measuring that also. Doubles my workload. So we're up to 5 watts again. And here SINAD is basically not impacted. The distortion profile changes on this thing. And the good news here is that we now get a ton of power. Look at this, we now get quadruple the amount of power and actually beat the benchmark HP2 both in power now and noise and distortion, which is just remarkable considering that this is a little desktop amp and doesn't weigh a ton. And the 279 watts should be plenty. Now it does double your cost because now you're using 2 channels for 1 speaker when you bridge them. But this scalability is just wonderful. And if I allow 1%, look at this, we actually get 300 plus 320 watts of power on this thing. So that's just wonderful. I will cover this in a future video, but up until now, you could critique and say, well, all your measurements have been with resistors, and speakers aren't resistors. They can act capacitive or inductive. Well, I've got a new speaker load that actually lets me dial in whether I want to have capacitive or inductive and by how much. And here you can see that I've run that at 8 ohm, at 4 ohm. The protection circuit on the amplifier was shut down, and because of the limitation in the software, I couldn't test it at 4 ohm. It wasn't the fault of the amplifier, but it just wasn't compatible with this kind of load testing. But good news that at 8 ohm, it did not care at all. I could make it fully inductive and fully capacitive, and it just didn't care. And you know, it ran fine. The load also can go all the way down to 1 ohm. So I did select 2 ohm, and at 2 ohm, the amplifier quickly shut off. So it didn't, you know, it doesn't support 2 ohms. But the good news is that when I'm running this test, it's really, really pushing the amplifier hard. It keeps pushing it to clipping point multiple times to try to ascertain the maximum amount of power that it can produce. and with capacitive and inductive loads. So if the amplifier is going to oscillate and things like that and kill itself, probably going to do that in this test. Now, it's not a full-blown reliability test, but it does stress the amplifier, and the amplifier got pretty warm when I was subjecting it to this test. Okay, so this is what a state-of-the-art amplifier looks like as far as measurements and so forth. It's sort of mid-level in pricing. It's $800 for 2 channels, and if you want to use it in bridge mode, you wind up at $1,600. So now let's go lower in price and see what we get when we go lower in price. For that, we have Fosi Audio's BT20A Pro amplifier. Company sent this to me for testing. It's a little guy, costs $100, although they have a $20 discount for ASR members right now, so you can get it for $80. And comes with a 32-volt external power supply, or you can get a 48-volt one, which was my favorite. That costs you an extra $40 to get. And you can see the size of the power supply. They're much bigger than the amplifier itself. The amp itself is tiny. And there are a lot of these amps on Amazon, AliExpress, and so forth. But what distinguishes this amp is that they listen to us, or me and others, complaining that whenever these things have tone controls, you set them in the middle, they don't generate flat response. You have no idea what the frequency response of the amplifier is, and it's never flat because the pots that they use for these things are not calibrated. This company actually worked hard to make sure if you set these things to the center detent, it actually produces a flat frequency response, which is quite nice. And so I was happy to see that. So we go ahead and run our dashboard again. And again, remember, we have 1 kilohertz tone in here. And look at what happened to the noise floor now. Instead of being way down here and buried at the bottom, now we've got a lot higher noise in here. We have some unknown spikes in here. I don't know what the causes for these things are. Then we have a dominant third harmonic in here, and not much else in here. The third harmonic is now at minus 90, whereas before with the other amplifier we're at minus 125, so quite a bit higher. But again, remember, it's only spending $100 for this amplifier. The gain is 29 dB. I explained a lot of amplifiers have higher gains, and THX has a standard for amplifier gain is 29 dB. So whenever I have a choice, in this case I had a volume control, I set it to 29 dB. You could argue that since the other amps are now at lower gain, that maybe you get a little bit better performance if I set them lower. And it would be valid, but I don't know how to solve this problem where every amplifier has a different gain setting. Okay, so this is with a 48-volt power supply. In this case, I had to repeat every test, then plug in 32-volt power supply. And luckily, the sign out did not change at all. Now, look at where this little guy, for $100, look at where it landed. The median is somewhere in here. And you can see this amplifier, despite being only $100, is way above average in this green category, which I call very good category. Blue is really state-of-the-art stuff, but I like to see an amplifier land in this green area. And a lot of times, a cheap amplifier will say, "Oh, look, it only costs $100. I'm down here." But no, I mean, this shows that you can be up here. These amplifiers, by the way, use ICs from companies like TI, ST Micros, and other. These are major companies that make amplifier ICs that go inside smart speakers and boomboxes and things of that sort. And these companies put them in a standalone hi-fi amplifiers in here. So their job is to extract the best performance they can out of this silicon. And in this case, clearly they've done a decent job in here. Now this graph is an eye chart. You can click on it and rotate it yourself if you want to look at all of them in here and every amplifier is in here. Or if you just care about what is the neighboring amplifiers in here, I zoom in and look at this. This is a Denon AVR. I think that's a $1,500 AVR over here. And there's another Denon here. Look at this PS Audio M700. There's a company sell you, a expensive amplifiers and tell you that, you know, they're great. And yet when it comes to noise and distortion, this little $99 box, you know, matches or beats them. You can see other ones over here and you know, what's down here. Okay, so we also then go look at the noise performance. We only get 84 dB. I like to see 96 dB here, by the way. So 16 bits, same as a CD. This is 14 bits, but you know, we're talking about $99 amplifiers. So for the class, it's pretty good for a budget amplifier. Where, you know, price of 2 or 3 fast food meals. You know, you get there. If you go to full power, it actually clears the 16-bit hurdle. So this is quite good for, you know, if you use a typical speaker, you shouldn't be hearing much hiss out of it. But we do have a problem with these IC amplifiers. They're all Class D amplifiers, and the Class Ds have this carrier switching frequency that's, you know, above audible band, and it's part of the operation of the amplifier. But to you don't want to release an amplifier with that noise coming out. So they put a filter in there, and that filter then becomes in parallel with your speaker load and can change the frequency response. So at 4 ohm, we see a response that, yeah, it's not ruler flat, but it's only 0.7 dB down at either end. But if I change it to 8 ohm, look at the large transformation in here. I shouldn't say large. I've measured other amplifiers where this thing peaks way the heck up here and comes down. This is a very amplified scale. It's only +5 or -5 dB. So this is zoomed in. So worst case in here, we got 1.5 dB of peaking, and that happens around 60, 70 kilohertz. At 20 kilohertz, it's only half a dB or 1 dB higher. So yes, you're going to get low dependency. So some speakers you hook up to this amplifier may sound a little bit more bright or a little bit more muffled, depending on how good your hearing is. Most of us are older, we're down here, so the difference is much smaller. But, you know, ideally you want to get a flat response, and to get flat response, you have to pay more. There's no $99 amplifier that I know that can produce a flat response with as much power as this guy does. You can get a Class AB amplifier that's fine, but you'll pay penalty in available power, as we'll get to in a second. Okay. Multitone, an entirely different picture than the Topping. We're not in the same class. So we see that the noise floor has gone way up, and there's spikes here and there. But where our hearing is most sensitive, again, is around here. And if I compute the dynamic range, we're talking about 14 to 17 bits of distortion-free range. This should say distortion-free, not dynamic range. So, you know, it could be a lot worse. You could be, you know, down here where you got severe distortion. You know, over here, you know, you're getting competent performance, but you're not getting state-of-the-art. So that's what a sort of medium or above medium level device performs. Crosstalk is actually excellent. Remember, this is a $30 amp that looks just like this one, and look at how bad it is. This one has very good channel separation in here. This is where the killer surprise for me was for this little amplifier, was that with 4 ohm, and I believe this is with 48 volt power supply, it produces 146 watt stereo. This is, all these graphs are in stereo. So it's essentially 300 watts of power is coming out of this little $100 little box this big. It's just insane. And its noise actually quite good. Distortion takes over when this graph goes up, remember? So up to 20 watts is basically, noise is your only issue, but as you go up, it starts to creep up, and then this going backwards means the protection circuit, the limiter, has kicked in to protect the amplifier and won't let it go any higher than this. So you don't want to operate in this region. But boy, 146 watts of power. And if I allow 1%, that was already at 1% up here. We don't get much more. But look at the burst power. Burst power is 180 watts per channel. Now we got talking 360 watts total in stereo coming out of this little box. Well, yeah, you got a 48 volt brick power supply. So even with the 8 ohm now, you have decent amount of power, 70 watts of power coming out of this thing. And I did go run this thing at 1% for 8 ohm. Oh, no, sorry. This is for the 32 volt power supply, which is stock with it. So 32 volt power supply, you know, does give you less power on this thing. So you do want to get the 48 volt one if you want to be serious. So in fairness, it's $140 amplifier. minus $20 if you buy it with the ASR discount code. Okay. We switch to 8 ohm over here, and you know, we lose power obviously, but you still 100 watts of power, and with 32 volt power supply, we take a big hit because the higher the impedance, the more voltage you need in an amplifier. So the 32 volt one really takes a hit in power, but the 48 volt one still breaks 3-digit numbers as far as power. Okay. Now, remember on the topping, when I changed the frequencies, all the lines were on top of each other. Not so here. The higher frequencies generate higher amount of noise and distortion up here. But as I go down here, it gets lower and lower till I get to 20 hertz. And 20 hertz, this orange line gets a lot worse than it goes back up here. Luckily, it produces almost the same amount of power, about 90, 95 watts of this thing. So for this class, this is actually quite excellent. The fact that these are smooth is quite excellent. So very respectable for a little budget amplifier. Okay. And this is the on-off performance. I won't dig into it, but you can see what happens when you turn it on. And notice here when I turn it off, now we're up to 10 or 15 millivolts. And indeed, I hooked it up to my Infinity's tower speakers, and I could hear a faint tick. So just to calibrate your ears, that about 10 millivolts is audible on, you know, sort of typical speaker on this thing. Okay, so that was our second example. We're sort of middle of the road, but budget amplifier. But now let's go to luxury products. And here we have a beautiful Luxman amplifier, the SQN150. Tube amplifier, beautiful VU meters, small but nice. It costs $3,300, so a lot more expensive on this thing. I won't bore you with the details in here. They even are nice to show a block diagram and rough schematic in here, and so if you're a tube guy, you can dig into that. So let's look at our dashboard again. Boy, is the picture different now. We're still at the same 5 watts, and we've got the 26 dB of gain. But look at what happens. First of all, we have all this power supply noise. You know, there's no reason to have this much power supply noise at just 5 watts. All of this with good design should be suppressed down to nothing. Just because you have tubes doesn't mean you can have all this power supply noise. Yes, there are some tube designs that generate this, but you want to avoid that. I don't care who you are. You can't make a case to me that listening power supply noise and harmonics is a good thing and makes the amplifier more musical. It's just not going to do that. And the notion that harmonic distortion out of tube amplifiers is usually just second harmonic and therefore that's more pleasing and doesn't have higher order ones. Well, this one has higher order ones too. It's got one at 3 kilohertz and then a bunch more that go on to infinity over here. So very bad showing. So we combine the noise and distortion together, and I assign that drops to effectively 48 dB, and look at where it lands. That's the second worst amplifier I've ever measured as far as noise plus distortion. So we had a $100 amplifier here, and now we got a $4,000 amplifier landing way down here. The dynamic range actually surprisingly wasn't as bad as I thought it was going to be, about 85, 86 dB. I've measured worse, so this is not bad, but obviously, you know, you want state of the art at these kinds of money. Frequency response is not flat. It's got some kinks in it, but luckily within audible band it's more or less flat. So from that point of view, it's good. What's not so good is the crosstalk. Look at what the crosstalk looks like. Usually crosstalk gets worse at higher frequencies because of stray capacitance causes higher frequencies to couple between the channels more than lower frequencies. This one actually has constant amount of bleeding from one channel to the other. That tells me that there's basically a direct path between the left and right channel. It's just broken. This should not happen. Not in an absolute level is low enough, probably not be an audible concern, but from an engineering point of view, it's just awful. So whoever takes this amplifier and raves about how his sound stage is better than solid state amplifier and so forth is quite wrong, because this is actually bleeding from one channel to the other. So if anything, soundstage should be worse. Then we get into multi-tone, and what a disaster we have in here. Worst case, which is down here, we only have 7 bits of distortion free. Best case is only 11 bit. So if you're playing music and it's got all these notes playing, you have so little clean sound coming out of this amplifier. All this is masking and destroying the low-level detail in your music. All the music detail in here is just stepped on, stomped on by harmonic distortion and intermodulation. So again, somebody waxes poetic about this amplifier, being so musical, and they can hear all the details. They can hear as if the singer is right in the room with them. No, you're not here doing any of that, because look at how much intermodulation noise this thing's generating. And the more tones you have, which music has thousands and thousands, or close to infinite, then the worse this gets. So definitely not a case of goodness in there. Now, bad news continues. Look at the graph now. We have low noise dominated up to maybe 1/5 of a watt. Starting at 1/5 of the watt, we haven't even gotten to 1 watt, distortion starts to take over. And typical of these kind of tube amps and low feedback amps, distortion gradually rises, but it starts so early, but by the time we get to max power, we're way up here in distortion. And we only got 12 watts of power out of this thing. 12 watts. I mean, that's like candlelight level power as far as I'm concerned. I don't know what kind of speaker you have to drive. They only need 12 watts. And then at 12 watts, you got all this distortion you're pumping in. Clean power is less than half a watt. I mean, that's what, and even that's not clean. Look at how high this is relative to our referencing. On this thing, 8 ohm, sorry, this is 4 ohm. That was 8 ohm, and this is 4 ohm, and same bad picture in there. So now we got only 10 watts of power. Allowing for more distortion doesn't help you. It actually penalizes you, because those graphs actually more than 1% harmonic distortion. So only got 11 to 12 watts. You got this giant big chassis. It looks beautiful, but for what it's supposed to do, it can't do. And look at what it's doing now. It linearly increases distortion with frequency, goes up. They're smooth, which I guess you could say is good, but they're so high, these lines need to be way down here, not way up here. And look at what it does at 20 hertz. It's definitely not happy driving low frequencies at all. And so, you're raving about the bass there. I don't know what to tell you. I won't get into the phono stage. We'll do another video on that. There's a headphone amplifier, and I'm not going to talk about that either. I do, whenever I see something this bad, I do perform listening tests. And in this case, I just not having enough power was just so apparent to me that you just turn up the volume, and as I noted here, you actually literally it starts to crackle on this thing. But if you lower the volume, it just sounds awful on this thing. And I did an A/B comparison to make sure it's not me, and I put a Topping PA5 in there as a replacement. And the boominess I was hearing, I was no longer hearing it, which tells me that the frequency response of the amplifier had modified based on the actual speaker load that I was connecting to it, or the harmonic distortion out of that 20 hertz. This poor performance here of 20 hertz was causing more room modes to be activated. So to me, it just sounded horrible. You basically had very little volume, was kind of okay, but anything more than that, it was just a disaster. Yes, if you have a more sensitive speaker and you don't play as loud, maybe it's okay, but I certainly heard no magic. There was no tube magic to me or anything like that. Now, you're welcome to ignore my subjective remarks, but I put them in there for people. So while you're just measuring, you didn't listen. Well, I do listen when, distortion is so high that it's good to quantify, qualify them in this case. So no recommendation, obviously, on this thing. So another long video, 49 minutes. I apologize for that, but hopefully with these examples, you got a good feel for how powerful measurements are again, how nicely we can quantify how noisy a speaker is, how transparent it is, what its tonality is, how much power it has. And, and this information you cannot get out of manufacturers, unfortunately. Even the ones that give you a spec is sparse. You don't even know how this stuff was measured. Anybody ever complains, by the way, saying, oh, your measurements are wrong, here's my data, ask him for graphs. One number means nothing. What if I just told you this amplifier produces 12 watts? That tells you nothing, until you look at this graph and say, whoa, forget about the 12 watts. Distortion started at half a watt. This is super important to see. So, you want to see this kind of measurement. And so manufacturers says, nah, those ASR measurements are not accurate. Here's my number. I've got 0.01% distortion. It's like, what does that mean? That doesn't mean anything. What are the conditions in here? And you want to get the conditions of the test, and that's what determines then, what the value would mean. And you really want to see the full sweeps at many different data points in here. It's not just one number. A lot of people say, oh, you go all about just sign-out. Like, no, that was start of the story. But even that wasn't the start. The start was this picture. First my eye goes in here and says, all right, what are we producing that we don't want? All this junk we were producing we don't want. So yes, that translates into cyanide, but then we went on and on and on and on and on and on, and we keep looking at the amplifier from a different vector, different test conditions, and at the end a picture pops out, and a picture that pops out of this amplifier is that it has no redeeming quality as far as audio performance. It's gorgeous to look at, and if looking at it, and it's important, which it is to me, by the way, then you're golden. This is a gorgeous amplifier, much prettier than the other 2 amps that I showed you. But the moment I hear it, to me, it's like, whoa, I will never turn this thing on. Okay. All right, so we'll continue on to cover the other categories in future videos. Thanks for being patient and listening to my long presentation. Okay, bye-bye.